Okay, hi guys. Today we're gonna review our solutions for the advent of code. We already caught up with day 14, so it's half the way through all the challenges. We solved all of them, right? But so we're gonna just review the solutions to them because it's like took a while to solve some of them, so we didn't live stream. So maybe I had to review what was the first challenges for because I already forgot about the problem. So maybe it will take some time for me to just remember what was happening. But okay, we're gonna start from day 5. So what was the problem? As before, we already have some summarization done with LLM. Maybe it will help me to remind myself. So it's some kind of graph problem, right? We have a list of rules, we have a list of updates, right? And we just need to rules define updates. From the rules, we can construct the graph. Let me just rerun all of this. Oops, I press the button. So we have the graph. Let me look at the graph. Well, it's almost complete graph, very dense graph. From the graph, we can just extract the adjacency matrix. And that adjacency matrix, we just can use it to determine whether we can travel from one vertex to another. And I guess that's what we basically check for each update. What was the updates? Updates is just like some sequence of vertices in this graph, right? So for each sequence of vertices, we just for each of those, so if hash is the int, we just fold over it, I guess, until we reach the 0. We just check whether those are adjacent or not, just do something, and then I guess we do extract the middle one. Yeah, and if it actually was ended in 0, we just return nothing. And then we sum it up. So it's a pretty straightforward one. Just a nice use of graphs. The second problem was maybe more challenging. It involved some actual graph algorithms like finding Hamiltonian paths, but it also was very easy to do because we didn't have to code it from scratch. So we just had a convenient function to extract the subgraph from all those updates, right? Updates is just a list of vertices. So given that we already have the graph, I think here I just highlighted all those updates, right? Each color is just one of the subgraphs like this. So given a subgraph, we order those. Essentially, that's how we order those, because that was the problem, I believe. Because those updates in the first part of the challenge, we dropped all the updates that weren't ordered, right? But in the second part, we should order them so that we can actually traverse those updates across the graph. And that's what Hamiltonian path would exactly do for you. As soon as you extract the subgraph itself, you just find the Hamiltonian path in this graph, and you get the ordering that you desire. And yes, and that's basically you do the same thing as in part 1. Extract the middle update, I think. And that's it. And just do the total, get the answer, post it, and it was correct. Okay, so that's it for the day 5. Okay, day 6. That's my arch enemies. For mark enemy nemesis, I guess, arch nemesis in this kind of year, because it was the most difficult for me. I still don't know the nice solution for part 2, right? So it really bothers me. But the gist of it, right? I guess it's like one of those labyrinth problems. You have a grid um, where you have some walls in it, and you start from some point in that labyrinth, which is supposed to be a guard of sorts that is walking around this labyrinth, and it also has a direction. So I guess I just colored the direction here. So the cyan color corresponds to up direction, so towards up of the screen. So the guard starts walking up the screen. As soon as he encounters the block, this barrier, whatever that was, a wall, he just turns right until he encounters another wall, turns right, and so on. So he's turning clockwise as soon as he encounters some barrier. let me see. Let me parse this. See what it works. So this is the initial guard position. This is his initial direction. We can just for convenience record all the moves: left, right, up, down. Some other convenient functions to check whether we're still in the bounds of this labyrinth and we haven't escaped, because I think the first challenge was simply to, this is just me playing around trying to come up with some clever graph solution, because that's our favorite to do, to just play around with graphs. So, but I didn't find out anything interesting about the graph itself and how we can incorporate it into solution. But anyway, that's the graph. And I guess the first problem was to simply trace the trajectory of the guard through the labyrinth and how many unique positions the guard would explore while he was, until he just leaves the labyrinth, escapes it, right? And that's like, I think that's the path. That's the path, but we had like a much nicer visualization for it. Here it was, was the starting position. This shows first trajectory until the first barrier has reached. This is the second one. He turns right, you reach this one, you turn right, turn, you again move to the left until this one is reached, and so on. And you walk around this labyrinth until eventually you escape it. And you escape it there, over there. So it's like, that was the last loop that the guard did. So just around 155 lines in total. Those red dots are just our attempts to come up with a clever solution for part 2, which we still haven't figured out, but we just, at the end, we just brute forced, because the brute force was, basically the problem was, is just to find a single position of the barrier that you can put on the path of the guard, so that it could just change the trajectory so that it will loop indefinitely. So instead of just escaping the labyrinth there in this point, he would just loop around, basically traverse the same path over and over again, right? And we just allowed to put one single barrier, and the question was how many possible solutions for that. So how many options, how many how many positions you can put that single barrier in order for to guard, to trace the cycle. And we've tried like to come up with some clever solutions, like finding the intersections. That's what those red dots are, trying to compute the intersections of some lines that you can just put like extend in the trajectory of the guard. You can extend it to the whole line between one block and another block, and like the intuition was that when those lines are intersecting, that's kind of an indicator that you can put a block there, so that you can send the guard along the same line that he already traversed in the past, something like that, right? But it wasn't enough. It was, you have to do it in a more recursive way, so it was not as simple. And it seemed like and it still seems that there is like a simple solution to it, but we haven't found it. Maybe we should just search for it. I'm sure there is one. So in the end, we just brute forced it. We just tried all possible um, barriers on the path, right? On that path that just of the first part of this problem, right? Because we don't have to consider all of the positions. You only have to consider the positions along this path, which at least the simplest optimization you can do. So we're just searching along that path, and we just try that abstraction there, and just do some simple loop there, just that tries to detect the cycle using just recording all the visited positions that we already traversed until we loop, and then just count it. I know what this, whatever. Yeah. So at least we know the solution, but the solution that we tried to recover from counting intersections was too low, so we just gave up. Maybe someday we gonna, I don't know, just return to this problem. But for now, just let's go on to the next one. So the day 7. So day 7, oh, that was pretty straightforward. We could have done something more clever, but Wolfram Language already provides a good solution, good enough solution for it, so it just don't have to bother. It's just the problem was um, given the input, which is what was the input? The input was just a bunch of numbers and a target number, and you simply have to do like a basic mathematical problem that children solve in schools, like put some algebraic signs in there, like minus and plus or multiply. What was the signs again? Yeah, you're allowed to only put the plus and the multiplication, so plus and times. That's for the part 1. You're only allowed to put 2 signs in between those numbers, and there's no parentheses even, so just a orderless algebraic computation of those numbers, and that's the number that you have to reach, right? And I think it's guaranteed that there's always a solution, or maybe it's not. At least, you have to throw them out if the solution does not exist. But here's just a brute force. It's just you can generate all the possible combination of signs, right, with tuples, and then you just fold over those and just perform the operation and see whether it's equals to the target. Any of those is the target, right? And then we just compute how many of them they are. Or we could, I guess, we sum up the targets or something like that. And for the second part, you simply increase the complexity by introducing a new operation, which is just concatenates the integer. I don't think there's like a nice integer join function in the language, but so just you can write it like this way, or you can do it, or you can write it by converting it to a string and then concatenating the string and turning it back to integer or whatever. But the gist of it, you just have to, simply a fraud operation that you can perform, and you do the exact same thing and also the exact same thing and compute how many solutions are there in that list that you are given. Pretty straightforward. All right, for the day number 8. Okay, what was that about? Don't remember. No, so this is those are the antennas. The antennas thing. So I think you're basically given a grid of dots which do represent an antenna of some different types. So here's the color. I guess it's just if it's the same color, that's the same type of antenna, and all you have to do is to put like an antinodes around those antennas in some specific way. Basically, antinodes at a position. If you're given a pair of antennas at position P and Q, right? The antidotes are those simply that are the same distance away from those 2 antennas, which is the distance between the antennas themselves, something like that. So we compute the distance, right? This is the difference vector between those, and just 2 antinode positions are simply computed by that, like that, and you just filter out whether you go outside the grid, right? This is just a helper function to filter out whether it's inside of that grid or map, and then you just do some basic, I don't know, just data wrangling, I guess, of those antinodes at each position. What is this? Oh yeah, because there are because antennas are not just pairwise the same. There can be 3 antennas of the same type, so you have to compute all the subsets of size 2, which is basically all the pairs of the same type. Compute the antinodes, concatenate them together, group them, blah blah blah. Compute the unique antinodes because some of the antennas have antinodes in the same place, and just count the number of those. And for the part 2, what you do, I think, is a bit more complicated because you don't just place the antinode a fixed distance away from the antenna, but you do it like in a continuous fashion. Maybe there's an example here when they show that. Yeah, so if T is an antenna if this is the pair of antennas, in the part 2 you would just put an antinode here, but in part 1. But in part 2 you would continuously put more antinodes the same distance away, so just until you reach the boundary, so until there's still a place on the map that you can put one in. Yeah, so not too much complicated. More complicated, you just use nest while, so that you start putting the antinode until you actually reach the boundary, right, in two different directions. So very straightforward. Then you compute the answer. That was day 8. Right, day 9. What was that about? Okay. Let me see the prompt. What was that? Oh, that was the fragmentation. Okay, I remember that. That was a fun one, because it actually involved some conventional programming, you would say. It's like I actually had to write a loop. Maybe it was maybe there was a better solution for that using more functional programming, but anyway. The point is you had like a specific representation of some data layout of your files on a disk. Say like this, like for example in the part 1, the layout looked like this, right? I think it just says you have a file with ID 0, then some 2 empty spaces, then the file with ID 1, you have like 5 blocks corresponding to that file, then there's more empty space and so on. So you have this layout of file IDs in your disks, so you can, so for the part 1 you just simply compute positions of empty spaces of files and just do, and you just I think the problem was to just move around those files into the empty spaces to the left of those. There was just some wrangling of those, just changing the layout itself. The layout was pretty large, so I guess that's the only problem. Maybe just moving around this, maybe not that large, but moving around and changing layout itself, it was not ideal. But for part 1 it was pretty much sufficient, right? You just folded all the file positions and changed the layout by replacing empty spaces with files and changing the list of files that I have to fragment and so on. But for part 2 is in order to be efficient to actually solve it in the reasonable amount of time. I used a different layout setup. So the layout, it was still kind of slow, I guess, but not that slow. as you did I actually execute everything? I don't remember it being that slow. Okay, that's fine. 10 seconds is okay. So the layout was, oh, it was kind of still terrible. I was just recording the ID and how many of the blocks they are. ID, empty space. Empty space is just how many of those there are. So if it's a list, then it's ID of the file and the size of the file. If it's just the integer, then it's just how many empty blocks are there. And I just modify this directly by using inserts. Like I could definitely like speed it up by not using position and searching for the layout every time, searching for a particular ID. You could use some data structure, but yeah, could have been bothered by that. But basically, as soon as you run through all the recommendation steps with that loop, you modify the layout, and then there's just one simple fold through it to compute some number that is required to solve this challenge. Yep. Yeah, that's fine. Day 10. Okay, another map. And another, what was that again? What was the problem again there? Let's see. So, oh, just yeah, it's a pretty much straightforward graph problem. You're given a map, which like a height map. I should make a nice visualization for it. Instead of, so map is just a list of integers, What if I do list plot 3D, interpolation order 0, filling bottom, yeah, something like this. A 3D picture of, so that it shows the heights. So basically, you're given a height map of some land, whatever, right? So this is, and you mountain terrain basically. You're given a mountain terrain with some increasing heights, and you just were asking whether you can traverse it or not, or count some paths for it. So basically, the solution is just to make a graph, so that each edge corresponds to in increase in 1 meter or something like that, just by 1 unit of height, right? So that you can traverse it. So that's the only allowed move that you can do. You can increase your height by 1 unit, and you can put an edge in that position. So basically, I constructed it from the grid graph. It's like some surgery on the graph. You start with a grid graph of the size of the map, and then you just remove all the edges that are disallowed, that correspond to a movement that is higher than 1 unit of height. Yeah, so you do, this is just change the name, and then you place it. Yeah, something like this. This is computing exactly. This is the height. This is the height difference. If it's 1, then you put an edge. If it's -1, you put an edge in a different direction. If it's anything else, you remove the edge. And you just get this disconnected graphs. You can also highlight all the zeros. It's the lowest position on the map. 9 is the highest position on the map, right? And the question is basically, given this map or the graphs, obviously you can compute the distance matrix and just compute whether you can, how many ways you can go from all the zeros to all the nines, something like that. Second part was not much more complicated. As soon as you have a graph, just instead of, I don't know, it just involved computing how many paths you can do in general, not just, what was the difference exactly? Yeah, I guess the first part was just counting whether you can to go from 0 to 9, and the second part was whether in how many ways you can do it. Yeah, and you just can do, because you have a graph already, you just do find path and just count all of them, compute all the paths, take the length. It runs almost instantaneously, so it's not like it's too complicated of a problem. All right, day number 9, which is kinda is supposed to be very nicely formulated for the Wolfram language, because it involved like some rewriting rules, almost like on a list of numbers, which are supposed to be some stones with the number written on it, right? And there's some specific list of rules that you should follow. I guess if you summarize it, the list of rules is basically this, right? If the stone has the number 0, or is the 0, it turns into 1. If it's even, then it splits in 2 stones. If it's neither, then it's multiplied by 2024. So just have these rules. I guess I just encode it by simple which. Maybe you can make it cleaner, but it's fine. If it's 0, then it's 1. If it's even, if the length of the digits, right? You compute the digits first. You split it in 2. Basically, that's how I split it in 2. And just splice the digits, and other cases you just multiply the stone by this 2024, right? And then you get the after 25 steps, you have some large number of new stones, just a list of these numbers, and the question is just to count them. But the problem was that it's not very efficient, because the number of stones actually increases exponentially or something like that, because there's some possibility of increasing twice, right? You're splitting the stones, so it's not exponential, but at least it's okay, it's increasing. So it's much more complicated doing it. The more steps you go, the more step you do, the more complicated it is. And the second part was simply the same question, but do it for more steps. Instead of 25, you have to do it 75 times. And this naive solution wouldn't work because that list is gonna be, it's too large already to be reasonably computable. So you had to be a little bit more clever here, and you just instead of using the list itself, you just make an association that counts those stones, because you actually don't care about the positions of stones. You just, because you always do just splitting all the stones and replacing them, so we don't care about the sequence anyway. So we just make an association of counts, tally them, and just make a clever modification of that tally so that you don't have to recompute the same operation or apply the same rule more than once. Oh yeah, sorry with that. Okay, James. Just explaining some challenges. Um, Retrodictively, I guess. Retrodictive explanation of challenges. And basically that's the day 11. We just come up with more clever way of counting stones using association, so that we don't have to apply the same rule more than once on the same stone, keeping track of its counts. All right. Moving up to day 12. This is actually was more perfect for the Wolfram language. It's almost like because it involved image segmentation, and we basically in the Wolfram language there's just a single function that can do the work for you. As soon as you, maybe the difficult part was to actually construct a map, than to actually construct the solution, because what you are given is something like this, like some kind of map of letters that can repeat. So you can have the same letter multiple times, like K here is one region, but also see K here, which is another region. So we kind of have to come up with a unique ID for each of those regions. So we have to extract them. And this basically does this. And I did it like very similarly to one of the previous challenges, just making a surgery, doing a surgery on a grid graph, right? Just make a grid graph, again of the same size as the map, and then deleted a bunch of edges. I guess in this is much denser grid graph than before, but can still work. So so what I did, I basically removed all the edges that have the different, basically that have the different values, because you're only allowed to walk in the single region. That's how you can identify all the region. Then you just, as soon as I remove all those edges, I guess this is just gonna make a disconnected graph, right? Hold on a minute. So if I do this and do this, this just makes a disconnected list of subgraphs for each region. So it's not very interesting. Most of them just some path graphs, maybe a little bit more complicated than that. But the point is that you can then just take the connected components, and that would be exactly the regions that you require, and you in that way you can separate all the regions from the map. And then the answer to the question is just compute some measurements of those regions. And for part one is simply the area or the count of all the squares in each region, right, times the perimeter. So this is just component measurements, pretty simple, right? And for the second one, it involved some contours, right? The contours is just a list of lines that you can also extract with the same function, and that's like all the contours. So you can see that if you just think of those regions as polygons, that's not gonna cut it because there's some holes in them. So in a way you're it's making a hole in that region that is a completely different region that you have to take into account. So your perimeter, for example, would increase by 4 if you have this single cell hole in one of the regions. And so because there wasn't a ready measure that you can use from that function, but at least those contours are already half the way through. So after you extract the contours, you just count the number of lines in that, right? Because that would exactly count all the lines, including all these holes, because that would also count for the perimeter. So mesh cell count counts. The number one is the dimension. So basically, that function is going to count how many lines you have, one-dimensional elements or one-dimensional cells in this mesh, where the mesh is just a list of lines, and you do the exact same thing as before. You just count them up. Yeah. So that was day
That's pretty
12.
cool. I like that one. Awesome visual.
Yeah. Yeah. I think there's the you will like the last one that was today. It's kind of fun. So let's see. Yeah. Okay. The 13 one. It seems like it was straightforward use of optimization functionality, right? You don't also have to think too much. You parse the data. The data was simply like some vector A, vector B, something like that, and when the position was of the price. Yeah, and I guess was okay. Let me just the formulation of that I don't quite remember. Oh, you play in the claw, right? In like in those one of those arcade games. You play in a weird type of claw where there are just two buttons that move the claw in some direction, right? And you apply price is at some given position. So just given your shifts that you can do pressing a button and some cost for those buttons, because each of the different buttons has different costs. Like pressing button A costs you 3 tokens, and pressing button B, it costs you just a single token, and that's why it's an optimization problem, and you can easily encode it, right? As soon as you parse it, for example, this is like a configuration for the first claw machine, I guess, right? And for each of those, we just extract A and B as rows, turn them into columns. V is our unknown vector. That's basically how many times you press the button, right? This is just a positive integers, so you can easily specify that this is a vector of two positive integers, which we can just multiply our matrix of shifting vectors, right? And we want to give a constraint so that when we press it, we reach the price. So that's the constraint, and that's the quantity that we want to minimize, right? This is the cost for pressing button A, and this is the cost for pressing button B. And we just minimize it. There are some messages that we just quiet down. Then we simply extract all for some reason part 2 just asked, no, the reason is clear because minimization is difficult. Usually you just write some brute force solution here, right? That might be much easier when you have this additional constraint that you don't have to look for solutions that would take you more than 100 presses, right? So you can just try all of them and find the minimum this way. So you have to filter out, but we already used the most general solution you can do so, and the best one. So we just filter out all the solutions that are not part of part 1 and count them. And for the part 2, it's just the same exact thing, but now it's more complicated. You also put your price farther away to make it more complicated. Like what is this? 1 trillion, 10 trillion units away from the position that it was stated in the configuration, and you also don't have any constraints of how many number of presses do you need. So the number is much larger. So we wouldn't be able to brute force it. Well, here is like some kind of optimization, linear programming or whatever is required, and I'm pretty sure it's already handled by you for you by the Wolfram language. So it's very easy when you have the tools.
So is that
No
like linear
stressing out
regression,
about.
or what optimization is this?
Well, it depends on the input, right? It kind of minimizes a super function. It depends what type of input you produce. You put some constraints, because I put some constraints that this has to be positive integers, then it has to do some linear programming. I think, right? There's some special functions like you can call linear programming on your own, right? Linear optimization, I guess, which is a bit lower level UI for this kind of problems. You just, instead of letting it figure out what the problem is, you can use it itself. But I'm pretty sure this is it.
Okay, cool.
Yeah, you just give it the constraints, some cost things, and so on. That's just a well-known problem.
So how is this normally done if people are doing it in like a different language? Would they import certain like optimization packages, or would they have like pre-built stuff? Because this is nice that it's all built in, but how are people normally
Well,
doing this?
well, it depends how hardcore you want to be. Of course, if it's Python, yes, you can also import some scikit-learn function or something like that and do the optimization. If you want to challenge yourself, you write your own optimizer, and
Yeah,
I'm
I get
pretty
it.
sure people
Yeah,
do that. Yeah,
especially for speed, they'll probably have some optimized optimizer or something.
yep, yep. Because they also want to be very hardcore sometimes and to also challenge themselves to make every solution to run like in the fastest way possible on some weird hardware, even maybe like things like that. That would be very
And this
challenging.
was
It's like
and this was pretty quick the way you ran this optimization.
this one, yeah, this should be pretty quick. Let's run it. So you do the data, the part one, so okay, less than a second. So this one also less than a second. So it's fine, almost instant. And this is like saved more time writing it than actually running. So this is how you. That's why Wolfram language is good for just prototyping stuff. Maybe you do plan to make it hardcore and solve it by hand, also almost like in some very low level language. But you can at least build the solution and not compute the solution faster using built-in solutions and then just
Yeah.
compare. That at least will give you the reference point. Okay, I know the answer. Now I would try to make my own hardcore solution and come up with the same
Yeah.
answer much faster.
Makes sense. Cool.
Yeah.
Nice.
And the last one uh, came out today. We solved it a couple of hours ago or something. It was a very fun one. Hold on. This. So here you're again given some kind of labyrinth of sorts. Okay, what's the raw input? The raw input was just a map where each location is occupied by some kind of robot, and it has a velocity. So that's the position of a robot, that's its velocity, moving into some direction. Right, and there are a bunch of robots on the map. Uh, that's all you are given, and you have given the size of the map, and they're teleporting like the teleporting robot. They teleport from one side to another, and so I guess does this work? Yeah. Let me save the definitions. This is the map of the robots. When it's darker, it means there are two robots occupied in the same spot, which is allowed, and you just simply simulate it because you're given the velocities, right? So you can. That's how they move around. They just move given by their given constant velocity. And the first part was simply run it for 100 times, I guess, right? So here just multiply the velocity by 100 and see and just count how many robots there in like in some quadrants, something like that. it's not very important. I think the fun part was the part two. Was kind of creative one. Let me show you. So after you figure out how the robots move, you count them, how many of them in the quadrants after a given number of steps. And part two was pretty short. It's like it was to find the Christmas tree, right? A picture of the Christmas tree. So it asks you how many steps robots are required to make in order for them to be arranged in a Christmas tree. So you kind of given that there is some Easter egg, so that if you move the robots by some fixed amount of times, they're gonna be arranged in some nice pattern that looks like a Christmas tree, right? And you're given nothing else, so you have to come up with a way to find that Christmas tree, right? So, of course, you can like be very stubborn and just press this button until you see a tree, hopefully, right? But you don't know how long you have to click this. But
Do we have any idea of
what
what the tree looks like, or you have to kind of find it visually?
No, yes, that's the point. Was there's absolutely no idea how to find it. Of course, you can get lucky, right? And you just find it. Uh, but how I found it was kind of cool. It's like so if you just you make this manipulate button, right?
Yeah.
And there's a pretty good chance that you can find some good patterns already. Like if
Yeah, I
you
see there's some
quit,
stuff sort of lining up. Yeah.
yeah, like this band, like basically yeah, there's some
There we
flashing
go.
bands in there. Yeah.
Nice.
So and I found some numbers. Like this is one number that forms this band, right?
Uh-huh.
Uh, it basically took me a couple of minutes by just
Can you measure
dragging
the
this and
entropy? Can you like just use like an entropy formula or something and then minimize entropy? Does that work, or is that
oh
not?
I don't know how you would compute that, but I had the same idea. I actually made
Uh,
the entropy and it wasn't changing too much, so okay, I
okay.
will try something else.
Okay.
The point is that yes, by just dragging this thing around, I found this one, and I also found this number, right? So just found
Uh-huh.
this numbers that and it kind of makes sense that and then you just do some number theory. It's like it's you already from these two patterns you kind of can guess that probably it's some combination of those two numbers because the first hint was that the size of the grid was two prime numbers, right?
Mhm.
uh, and given that you found these two configurations, there's actually a Chinese remainder theorem that you have to use in order
Okay.
to basically you're gonna so you're given this size of the grid that is two prime numbers, and what you have to do then is to find a solution, find this number that is like solves this problem, right? These two problems over here. So I
Okay.
found this number and this number, but I want a single number that is modular the sizes of the grids gives you the same result, right? So that's how you could basically combine it. And the
So where did you
solution,
get this idea of a Chinese number? Like, how did you think of this approach?
I don't know, it's a common thing in this kind of challenges. I guess it's just experience.
Okay. Okay.
Yeah,
Okay.
yeah. I totally just fired my intuition there. It's just
Okay.
just okay. I just computed this. I got some number, and then I just put this number in here, and lo and behold, you get a tree.
Ta-da! Nice.
That
So cool.
that was a that was a pretty nice
Oh,
feeling.
nice.
I wasn't even sure about that, but
That's why the
that's
entropy wasn't that low, because there's still a lot of other particles floating around it. So as a
yeah.
whole, like the whole thing didn't become a simple shape.
I mean, what if you
Yeah.
do like run length encoding compression? You just try to compress like the output and see like which ones is less.
Maybe. I know. I think it's a cool change because it's creative. Maybe there's more than one
Yeah,
solution. You can do like some image recognition
yeah,
algorithm
exactly.
or whatever. You can fire all the tools at once. But I think that's something like this was intended. Maybe there's a better way instead of just of finding
Visual. Yeah.
these band patterns. I don't know, or some interesting ones, like finding this one more programmatically. I'm not sure. But yeah.
Nice.
Yeah. And that, I think that concludes it. So day 15 is not out yet. And this is it. This is a day.
Great.
We're halfway, more than halfway there.
More than halfway there. Okay, yeah. So that's the QR code,
Yeah.
and you can access this online, so anyone can pick this up and carry on. And we'll update the same link, right, with each of the challenges each day.
Yeah, it's the same link. I already uploaded it. So same link, like this link. You can just go there, just scan the code. It's always gonna be there, so you can check the solutions if you're interested every day, because I'm gonna keep
Very cool.
solving it and upload it there.
Nice. As the challenges get harder, it kind of the approach to solving them becomes more interesting. It seems.
Yeah.
You need
Well,
to
yeah,
use more
maybe.
intuition and more creativity.
Yeah, we'll see.
Great. Okay. Thanks so much.
Watching. Bye bye.
Nice. Okay.